In this video, we are going to be talking about measurement of the conductivity of ionic solutions, part 2. First of all, I'd like to say thank you to whoever's interacting with my content, like leaving comments, subscribing. It genuinely provides me the encouragement to continue working on this channel, basically. So in the previous video, we talked about two issues, like the first issue of using a Wheatstone bridge for measurement of conductivity of ionic solutions. So if you want to learn more about that, definitely check that out. In this video, we're going to be talking about the second issue. So this is the objective of this video. So we'll be so the second issue that I keep talking about is the fact that when you have an ionic solution, we can't really connect it to the Wheatstone bridge like this, right? So we obviously need to do it in a different way. If it was a wire or if it was a solid conductor, we could have connected it directly. But because it's a liquid, you can't really do that. So what we do is we use something called a conductivity cell. So conductivity cell is specially designed to measure the resistance. So these are two commonly used ones. It consists of two things. First of all, the electrodes which are present are platinum. They're made of the platinum metal, and they're actually coated with finely divided platinum on them. So the way this is done is by the process of electrolysis. And the reason this is done is this helps minimize the polarization effects. So the polarization effect, as you know, is the one that causes the change in resistance, right? So if because of the polarization effect, the in this space, what could happen is the concentration could vary, and because of which you might have a different resistance being observed. But in reality, it could be different, right? So because of this polarization effect, we do not use the direct current. Instead, we use the alternating current. That's what we learned in the previous video. So the electrode over here is the platinum metal, which is coated with finely divided platinum. And this is also called as platinum black. And the electrolyte is obviously going to be the salt, the electrolyte, the salt in the solvent that we want to measure it with. Okay, so basically we will be using the Wheatstone bridge. So first of all, you have the source, which is an AC source with a frequency of 500 to 5000 cycles per second. And we know why we're using the AC source. That's because we don't want the polarization effects to happen. The second thing over here is that R1 is a variable resistant. R4 and R3 are resistances that of like these are known resistances. And here we have the detector. Detector could be literally a pair of headphones because we can hear the sound. Okay, and this is the conductivity cell, that is the unknown resistance. So when we switch this on, what will happen is we try to change the value of R1 so that it gets to the null point. So at this point, what happens is we do not hear, as it is the minimum sound that is obtained. So what at this point we know R2 will be equal to R4 into R1 by R3. So we are able to calculate the value of the resistance of the conductivity cell. Okay, but the question is, how do we calculate the conductivity? So this is the basic setup of when we have an Wheatstone bridge and how we will connect it to the conductivity cell. So basically, it's a bunch of equations, I know. I know it's a lot, but first of all, we know that conductivity equals to 1 divided by resistivity. We are able to get the, um, and resistivity is equal to R into A by L. So, kappa, which is the conductivity, is equal to 1 by R into L by A. All we're doing is we're substituting 1 by this into this equation. So, we're getting 1 by R into L by A. So, L by A is the cell constant. So the letter L, it represents the distance of separation between the two electrodes. Essentially, this distance between the two, distance of separation between the two electrodes is shown by the letter L. And the A that we're talking about is the area of cross section of the electrodes. So we have two things, the length and the area. The length is the distance between the two electrodes. The area is the area of cross section of each of these electrodes. Okay, so we are basically we are able to calculate the conductivity equals to conductance, that is G, into L by A, which is the cell constant. So the cell constant unit is centimeter inverse, because if you think about it, length is centimeter, area centimeter square, so you're left with centimeter inverse. So conductivity is equal to conductance into the cell constant. So what we're doing till now, in the previous slide, we saw that we are able to calculate the resistance, right? So from this, from resistance is 1 by R, that's equal to the conductance. So we're able to calculate the conductance, and the cell constant is related to the length and the area. So the length is the distance of separation between the two electrodes, and the area of cross section of the electrodes is the A. Okay, now cell constant. That's a new thing that I just spoke about. So we cannot actually calculate or measure the length and the area of each of the electrodes, each of the conductivity cells. Imagine the amount of time it would take for us to actually calculate all of that. Instead, what we would do is we use a standard solution of KCl. What are we doing? We're using a standard solution of KCl. So we know at different concentrations, um, what is the conductivity of the KCl solution. So using that, we are able to calculate the cell constant of various conductivity cells. So what are we doing? We're using this standard KCl solution standard, whose conductivity and molar conductivity we know at various temperatures, and this is actually at a specific temperature but at different concentrations. So we are able to use all of this information, and we are able to calculate the value of the cell constant. Okay, so essentially we are able to, conductivity will be equal to cell constant divided by the resistance, right? So that is how we are able to calculate the conductivity. Now the conductivity of different solutions in the same solvent can differ based and at a given specific temperature. Obviously, the temperature is going to affect the conductivity. But if it consists of different electrolytes, you could have a different charge, you could have a different size of the ions, the concentration could be different, and obviously, even if you think about it, even if the size and charge changes, you will also have the ions which move under different, they will tend to move differently under a potential gradient. And because of that, we need another term of conductivity, which is molar conductivity. So the molar conductivity is basically the conducting power of the ions, where we have 1 mole of the electrolyte. So molar conductivity is denoted by capital lambda m equals to kappa divided by C. Kappa is the conductivity or specific conductance, and C is the concentration, basically molarity. So conductivity's unit is Siemens per meter, and concentration is moles per meter cube, or because we consider moles per liter, we're just converting that to meter cube just to have the units consistent. So we are left with molar conductivity's unit as Siemens meter square per mole. Now, obviously, we can also have it in terms of centimeter. And when we do that, when we convert uh, 1 Siemens meter square per mole to centimeter, we can just multiply it with 10 to the power 4. And when doing it backwards, we'll obviously divide it by 10 to the power 4. Or you can just say multiply it with 10 to the power minus 4. So I hope all of that made sense. So we started with figuring out a solution to the second problem that we had, which was we could not connect an electrolyte to a Wheatstone bridge. That's impossible. I mean, maybe. I don't know. So it's very difficult. So instead, what we do is we use a conductivity cell. The conductivity cell consists of 2 electrodes and the electrolyte, right? The electrodes made of platinum, which is coated with finely divided platinum, which is also called as platinum black. Now, when we connect it to the Wheatstone bridge at the null point, we're able to calculate the resistance of the conductivity cell. And I did talk about the Wheatstone bridge in the previous video. Definitely check that out if you want to learn that again. And from that, we're able to, oh, I guess this should have been here. From that, we're able to calculate the value of the conductivity. Conductivity is given by conductance into the cell constant, or basically conductance is 1 by resistance, and resistance is obtained from the Wheatstone bridge. The cell constant is a new term that we learned. This is basically L divided by A. L is the distance of separation between the two electrodes, and A is the area of cross section of the electrodes. And it's quite impossible for us to sit and measure each and every cell whose conductivity cell and try and figure out the cell constant. Instead, what we do is we use a standard solution of KCl, and whose concentration we know at different um, at a specific temperature. So using that, we're able to calculate the cell constant. So obviously, because there are so many variations we're observing, we needed a new term called molar conductivity. Molar conductivity is given by conductivity divided by the concentration, and its units are Siemens meter square per mole. I hope all of that made sense. In the next video, I believe we have a example problem that we need to solve.